Uh, Good afternoon, everyone. I'm Vignesh Ravichandran. I'm a PhD researcher with the University of Rhode Island, advised by Dr. Kunal Mankodia at the Wearable Biosensing Lab. I'll be sharing some of our research we've carried out along with the description on the journey. As part of my talk, I'm going to first start with an overview of what smart textile wearables are and what the advantages we get with it, and then cover a bit on the design aspects associated with it through uh, a detailed overview of two case study projects we've been working on. And I'll finally share some challenges and what opportunities our community has. So first, coming to an overall market survey, if we look at it, smart clothing is unfortunately not the most prevalent form factor. Uh, Instead, like the common form factors that are popular right now in the market seem to be smartwatches, wristwatch, and ear wearables. Uh, and a big part of that is the fact that there's a lot more challenges involved with smart clothing, but it's also what we have a unique opportunity to address some of those. And coming to what smart textiles actually are. Smart textile wearables refers to the integration of electronics or other active components onto a fabric to enable functionality. We had some earlier talks today about how that could work, and as part of it, you might have seen there's like different building blocks for smart textile. First is on the sensing side. We can have biosignal acquisition through ECG for heart rhythm, breathing, body temperature, but we could also sense the local ambient temperature and humidity characteristics. Apart from that, as Dr. Sun presented, we have like actuation potential too, where we can have vibratory feedback or thermal stimuli or lighting. And apart from it, another interesting characteristic of smart textiles, we had a good bit of talks on interconnects. So this is basically how we can bridge our soft textiles through more rigid circuits comprising of integrated circuits. So this we can accomplish through either snaps or magnetic pogo connectors, which we've been recently using, and conductive Velcro. Uh, at the heart of our smart textiles wearable typically is a control unit, which could be distributed through the nature of smart clothing, where we would have power and battery, processing capability, and also wireless and storage. So let's now look at what are the typical equipments we can use to make smart textiles. Typically, we use knitting. Knitting is largely used, and it basically involves integration of different yarns together. And this is a completely lossless process in a sense. So there's zero wastage in it, making it quite sustainable. But unfortunately, the machine itself is quite complex and quite expensive to obtain. But we can create fully ready to wear clothing articles with it, with integrated sensors and electronics too. Then we have embroidery, which involves integrating a thread onto a base garment. We had both Jim and Topher had presented their work too. But this involves a thread being attached to a base fabric, which is quite comparatively order of magnitude lower cost than knitting. Then we have a weaving, which is kind of similar to wind knitting, but we have a lot more yarns in the warp and weft, which we align. And the equipment as a result is quite expensive and inaccessible. And finally, recently there's been a new trend coming with screen printing or lamination. So any of you who have purchased any design t-shirts, you might have seen those print patterns that they have on those shirts. And that typically is done through a stencil where they drag colored ink. But if we swap it with silver stretchable inks or carbon inks, we can make entire circuits and electrodes with it. And it is quite inexpensive as an approach. So now coming to what unique advantages we get with smart textiles over regular wearables, it is a lot more comfortable and skin compliant. It can contour properly to our skin and ensure we have adequate compression, and it is also stretchable typically, depending on the base material we choose. We can ensure it's either stretchable or flexible. And technology like knitting allows you to have variable amount of stiffness in different areas. And we also as by its nature, clothing is something we evolutionarily have adopted in different body parts uh, from uh, from early on. So we can access different areas of the body. For example, if we needed to measure walking patterns, we could integrate sensors onto a socks, for example. Or if we wanted to monitor heart rhythm, we would go closer to the chest, for example. So also by its nature, compared to any flashy smartwatches, smart textiles have a unique opportunity in that they're more discreet. We can either wear it under our clothing, or we can either have the interface be more, if it's seamlessly integrated, it won't be as perceptible. Uh, and coming now to the design aspects of smart textile wearables, there's two important aspects we need to trade off. First is technical factors and and then we have human factors. In technical factors, we have to make decisions on what type of sensors we need to obtain, what are the interconnect types we have, and also what are the mechanical durability requirements we have. And on the other side, on human factors, we need to consider a lot on comfort, breathability, and also aesthetics. So I'll be now sharing the case studies. So this was a research project that was funded by the National Science Foundation, which basically uh, I started when I came here for my master's degree. And basically it was right around the start of COVID, and we were initially thinking of we were working on a glove for assessing symptoms of Parkinson's disease. But due to the constraints imposed by COVID, we had to pivot to instead make it a in-home acquisition kit. So we deployed a kit to patients with Parkinson's disease to have them to monitor their upper body movement symptoms remotely. So a quick intro to Parkinson's disease. Parkinson's disease is a progressive neurodegenerative disorder that basically has no cure. So because of that, the current interventions we have only seek to increase to slower the progression and increase quality of life. So it has a lot of behavioral and cognitive symptoms too, and there is a need to monitor progression. So talking about the progression of symptoms in Parkinson's disease, typically the symptoms start in the non-movement type, uh, and mostly it goes unnoticed and undiagnosed. But then people only diagnose when they notice movement symptoms such as resting tremors, after which the progression is pretty quick, and then over time it kind of evolves into movement disorders, gait disorders, and also instability, which leads to falls and eventually even fatalities. So there is a need to assess these symptoms, and currently the way clinicians go about it is through in-person assessment sessions where they visually inspect them while they perform certain hand movements or they ask questionnaires. But it of course suffers from subjectivity bias, and there is not as much resolution and time when we get these symptom data. So this kind of motivated us to create a glove for assessing fine finger movement and also overall wrist movement. And that's basically what I started out with. So me as an engineer, I came up with this glove. And for me, the main part was for it to just work at that moment. So mainly I worked on integrating these to a custom analog acquisition circuit. And then we basically were able to show that we were able to capture some symptom related changes associated with medication. Uh, and we were able to capture those changes. And we were able to collect this data from 4 patients with Parkinson's disease for a period of around 10 days before and after medication. So they would perform, we had a tablet provide the movement instructions, and we collected the data from our sensing gloves. And we were able to see that our gloves are metrics obtained from our glove data is able to identify differences associated with medication intake. And that was quite interesting. So that's where basically our study evolved further, because one big issue I ran with my initial version of my glove was my uh, patients with their tremor symptoms, ironically enough, were finding it really hard to put on the glove. Especially they would insert more than one finger into a single finger hole. And I realized we needed to improve our wearability of our gloves. So I had I then got to work with my with quite a large team of designers and textile designers, and we were able to apply some user-centered design principles to improve the glove design. So we started by first having observing our participants perform with Parkinson's disease, perform daily living tasks such as tying their shoelace, putting on like vinyl gloves, and cutting or using a zipper. So studying these videos, we were able to understand what kind of issues they specifically had and what kind of movements they preferred or didn't like based on the timing and what their subjective experience was. And then based on this, we were able to ideate and brainstorm potential design mechanisms, which when incorporated into the gloves can improve usability. So we were then able to leverage a rapid prototyping approach with the laser cutter to cut out the patterns of glove designs and then rapidly create 3 prototype glove concepts. And we basically tested those out with the participants. And as you can see, we first had an hypothesis that if we left the bottom part open, it'll be easy for them to put on the fingers one by one. But since we didn't give them instructions, we found that certain participants put the gloves in not the right way. But one of our concepts, which involved keeping a viewing window for the gloves, that considerably was quicker for them to do. And that's what we kind of then went with, and we integrated sensors onto it. So this is where we worked with Jim from Nautilus, and we were able to integrate a capacitive sensing thread to it. And then we were able to then test those on more number of participants and revise the gloves even further. Uh, so coming to the actual technology part we did for integration, so we approached this with late stage integration. Earlier, I had added resistive flexion sensors, which had more hysteresis and noise. So that's where we work with Jim to integrate their capacitive sensing thread, which could pick up the stretching associated with finger movement. And we found that it was quite accurate and higher resolution. Uh, and as I said earlier, so in this case, we use these magnetic pogo connectors, which are kind of straightforward to add to the textile and our circuits. So the second case study I'll be now sharing is a bit on the biosignal aspect, particularly with biopotential signals associated with the dry electrodes. So this study involved us fabricating different electrodes and evaluating the impedance characteristics with a skin agar phantom, and then exposing it to sweat and seeing how it changes its impedance characteristics right away and then after a controlled drying condition. And then we also evaluated how the signals are in for signal qualities for ECG. So coming to a big of primer on the skin electrode impedance, I know Dr. Sun had already covered some of this, but in a nutshell, gel electrodes we see commonly in ICU or emergency wards or even in Holter ECG monitors. So they're able to have really good skin electrode impedance because uh, they form a good contact with our skin, uh, including our micro ridges and pores. So this kind of reduces their overall skin electrode impedance, improving the signal quality. But but however, these electrodes suffer from usability issues such as skin irritation, and the gel dries over time, which affects its performance. So on the other end of the spectrum, we have the dry electrodes, which are made from conductive materials. Uh, and however, these electrodes have higher skin electrode impedance typically because they have a lot more capacitive gaps, and especially if they don't fit to the grooves of our skin, of the outer layer of our skin. So this reduces the signal quality. So I wanted to study how the design of the electrodes would affect it. So to fabricate the electrodes, we use the ZSK embroidery machine that Topher had presented earlier. And we basically stitched a pattern of different electrodes and using a silver coated polyamide thread. And other than that, we also wanted to test how a knit fabric would do, because knit fabrics offer omnidirectional stretch and conductivity. So we basically used a laser cutter to cut out a pattern after it was attached to a fabric double tape. And you can see a quick video of that process. Uh, So now that we had our electrodes, basically my main aim was to test out how the design characteristics of these electrodes would affect its impedance performance. So with certain electrodes like E1 and E2, you can see it has the spiral pattern, which was a preset available in the embroidery machine. And our hypothesis was that this would shorten the effective distance that any biopotential sensor would need to take to the measurement terminal. And then we also inspected patterns like comfort fill, which is basically a linear straight stitch, and then comfort fill plus is the stitch in two axes. And then we also tried to hybridize the electrodes by having a base layer of comfort fill with a crossball stitch on top. And then this is the laser cut electrode. As you can see, it has the net pattern on it. So to evaluate the impedance of the electrodes, we needed, with the skin, it's often time varying. So we needed a fixed measurement setup. And this is where I basically made a skin electrode phantom using agar agar with salt in a concentration similar to what we would find in human tissue. So I then carried out an impedance sweep from 20 hertz to 5 kilohertz at 10 hertz increments, and we were experimenting how like contact pressure would impact the sensor quality by simulating it with these slotted weights from 10 grams to 40 grams. Uh, and basically, these are the characteristics you can see for the electrode in their dry state. We can see that there's an overall decrease in impedance as we increase in weight. And we can see that within the electrodes, there's a slight difference in their impedance characteristics. And and this basically is after we did the sweat exposure and dried it, we found that there was a baseline increase in impedance, uh, which was kind of interesting. And this basically is the mean impedance associated with the different electrode type. Uh, for for all the contact weights. And this basically is the setup we use to expose our electrode samples to a synthetic sweat we made. So that basically you can see right after exposure to the synthetic sweat, there's a drop in impedance characteristic compared to the dry condition. And then after the controlled dehumidification, we found that there was an increase in the impedance characteristic, which I reported earlier. So this might be due to the fact that we have precipitates or solids, which are coating the electrodes, which affect its impedance characteristic. So uh, talking about the ECG signal quality, so we basically evaluated our signals using the BioPack bionomadic system, and we found you can now see all the different ECG signals. Maybe someone can identify which electrode is probably better in this case. Uh, so electrodes E2 and E7 have better characteristics, and that's what we noticed in our signal to noise ratio calculation too. So the laser cut net electrode and the embroidered electrode consistently were performing better in both impedance and the uh, uh, in basis of ECG quality. So now coming to some of what our learnings has been over time on this. So challenges we face is often in usability. A lot of it had to do with fit, be it for our gloves or our ECG based study. It affects both the variability and usability of these devices. So we could approach it through personalized manufacturing or incorporating adjustment mechanisms. So that could greatly improve its variability. Also, washability is a key constraint that affects this, and things like breathability could also be overcome by using more natural fabrics. And in basis of technical challenges, data quality is we can improve on the electrode end and the bioinstrumentation, but we can also look into more advanced signal processing algorithms and AI models to perform denoising or artifact detection. And as Dr. Sun had presented earlier, I think energy harvesting is a great avenue to go down, especially because of how lower power wireless and bioinstrumentations are becoming. And we can also use the large surface area we have access to with clothing. So especially if we use flexible or curved batteries, we could pack more monitoring time with that. And to address high skin electrode impedance, we could ensure that the electrode materials are more conforming to the surface, like conductive silicone, or even approaching it with semi-dry electrodes, which can be humidified if it's lower. So I was kind of thinking about the title of the workshop. So interdisciplinary research and collaboration has been a core part of all the work involved in making smart textile wearables. So often the needs comes from our clinicians where through talking with them, and we use our biomedical engineering knowledge to basically design bioinstrumentation circuits. And then we work with material science and textiles engineers to both evaluate our fabrics and suit and identify integration mechanisms. And finally, human factors and ergonomics community is also quite important in this, where they'll have a good bit of input on how wearable a device is. And finally, on data science and analytics, that also plays quite a crucial role. And this is where I was quite blessed to work with quite a wide team and learn from them. And I had the privilege of learning from all the diverse skill set all of them had, be it our clinicians or people who work on the smart textiles. So it definitely takes a whole group of these different skills to make a successful wearable. And with that, I'd like to conclude my talk, and I'd like to answer any questions.
Thank you, Vignesh, for the interesting talk. So right now we're gonna take some questions. Okay, I do have a question. In your electronic designs, you use different patterns, right? So do you have any findings on like how the pattern gonna affect your testing results?
Sure, that was a great question. Let me quickly share my screen again.
Yeah.
Just a second. So basically coming to the patterns of our electrodes, so that did play like a crucial role. So for example, the electrode E3, if we think about the conduction pathways a given signal might have to take, for electrodes like the base comfort fill electrode, it would need to travel a longer distance to get to the measurement terminal. Whereas like with electrodes E1, whatever sensed in the outer disk, that has a shorter path through these like spiral connections. So we found that those electrodes typically had better characteristics. So that if we see like comfort fill has like a higher impedance, but CB2, the cross ball stitch, which was the spiral pattern, that had better impedance characteristics. Uh, so definitely that was part of the hypothesis we had when going in, and we found similar result from our data. And knit electrodes too, they performed really well because of how the yarns are linked. You get omnidirectional conduction and stretching. So because of that, we have much lower baseline impedance with these knit electrodes too.
Thank you for the explanation. But from the results, I noticed E2 and E7 had, like let's say, as signal to noise ratio is pretty high compared to others. And so E7 is pretty straightforward because you were getting all the conductive stress or cover to the whole pads, is that right? And for the E2, that E2 is kind of similar design with the E1, but why the performance is like so different?
So with between E1 and E2, it has to do with the stitch length parameter we tweaked around with in the embroidery machine. So basically, with 2 mm, the loops are far longer. So my thinking on that is that maybe the moisture parameter, the moisture and sweat isn't as well collected in the tightly stitched pattern compared to the loosely stitched pattern that is E2. That was more my theory, but we need to still conduct further research to understand why that exactly is happening.
Yeah, got it. Yeah, thank you. Makes sense. Yeah. Okay. Thank you for the talk. And so right now we have all our four speakers represent in today's workshop. And so right now I will thank for the audience and for your participation. And if you feel any topic you are specifically interested, so feel free to reach out. And I think, and this workshop is recorded, so I think I will share the link on the website soon, and so we can have all back record on what we shared today. Okay, and thank you, and I think that's all for our today's workshop, and you guys have a good afternoon. Yeah, bye.
Thank you.
Thank you. Yeah, thank you.